uh,
Sorry.
for this seminar, which is a very good idea. And I would like to say sorry for the organizers for not participating before, but I will for sure make sure that I will participate in future events in this. It's just that I had to finish my thesis, and this is why it was a little bit complicated before. So my talk is going to be entitled Meromorphic Connections and Isomonodromic Deformations, History, Recent Developments, and Open Problems. So the point behind is that the point behind is that this talk will not go through the very much details behind this topic because it requires a lot of background and a lot of algebraic geometry, let's say. However, this talk is going to be some sort of an overview of the topic, the history behind the recent developments, and somehow I wish to transfer the ideas and the recent problems, open problems of this domain through my talk. So first of all, the talk is going to be decomposed into two main parts, an introduction and a background. The rich history of the topic first, and the primary state laid out by Riemann, the relation with the Pain-Levé program, and why this topic is sometimes considered also on not just algebraic geometry, but also has a lot of applications, fruitful applications into Hamiltonian formulation, symplectic geometry, mathematical physics, integrable systems, and many others. Well, but for some time now, we believe that the problem is actually blocked somehow from the mathematical physics side. And in order to get new insights and new things, this sort of a new modern point of view of the topic and the non-abelian Hodge correspondence has been developed. So this is the thing that I will try to motivate behind in this first part. For the second part, I will explain just on a general example what is actually going on and some results that we were able to obtain really recently in my PhD. So the three subsections of the recent developments are literally independent one the other. However, it's really if you know the general construction of 2.1 of general rank 2 meromorphic connections, you will be able to get actually the 2.2 and 2.3 pretty easily after. So this is the point. So I wanted also to say something before. My idea was for this talk is to do this first part, and then do an explicit example on my iPad, writing the things explicitly and showing you how things might pop up. However, my iPad broke down literally 2 days ago, so I had to take some slides from some presentation that I've done also in January this month. So you will find a little bit a change of design between the first part and the second, but the both of them will be the same exactly. So you will be able to follow one once and for all. So there are two drawbacks of this. One of them is positive, the other one is negative, honestly. The positive part is that the general rank 2 meromorphic connections, I will treat a very general example that we developed recently. However, the bad part is that I will go a little bit faster in terms of the things because there are some huge formulas that you will see later. So I hope this will not bother you guys. So let me start first by the introduction and background. So the first idea that I would like to address is the history, the rich history of the subject. So first of all, Riemann was the first to consider this, like in a lot of subjects of mathematics. He was the first to consider this problem of just a meromorphic differential system, what is known now as a meromorphic differential system, in his paper in 1857. And he said explicitly that, okay, if I consider such a system and I fix such a matrix L of Z, I would like to search for the solutions of psi of Z. And we know that these solutions exist because of Cauchy, but finding them is actually super difficult. And what he saw actually, and his idea was, if I deform the system in a certain way, so I consider deformations of the system, I will be able to get something very good and very fruitful. He did not continue to solve the problem. He just laid out the outcome of the problem. And he said that we will get very beautiful solutions out of this. And it was first two people who solved this problem. They are namely Schlesinger and Fuchs. They solved the case for the regular poles. So literally, when you have poles of order R infinity or RS in my matrix L of Z, which I will call pretty often a lax matrix. You will know the reason why later. So when I have R infinity or RS are equal to 1 or 2, not more than that. So they solved this system and they were able to get actually a very beautiful set of equations called the Schlesinger equations. So this was literally end of the 19th century, beginning of the 20th century. The problem, however, is super difficult when considering higher order poles. So for arbitrary R infinity, for arbitrary RS, this becomes way more difficult and it's actually not super easy to get. Here in my equation, just for clarification, the L infinity K and the LSK are just matrices, okay? And the Z is the local coordinate that I'm taking on the Riemann sphere for the moment. So just the complex plane with the point at infinity. So the problem is super diverse because a lot of people worked on it from different perspectives. So a lot of perspectives exist. A lot of them are from algebraic geometry, from mathematical physics when it comes to applications, and a lot others. But let me just say that the way and the title that I used started immediately with isomonodromic deformations. So isomonodromic really, what is really isomonodromy? And what is really behind this? So what is actually a monodromy? And how do I deform the system while keeping the monodromy preserved? So this is the next slide, which I will be considering an example of a monodromy. So very vaguely speaking, when I fix poles, so for instance, what I did in the previous slide, I fixed some poles which were located at the x-axis and at infinity, and I said, okay, I have this system, I would like to solve it. But however, let me see. So if I deform my system, how do these poles affect my system exactly? So this is the point of monodromy. So the monodromy is just a way of saying how the thing would behave if I consider taking it around a singularity. Okay, so this is a very pure example. This is a very straightforward example, which if I take f of z to be log z on the domain E with real of z bigger than 0, if I just deform this, so I have a singularity of log z on 0, right? So if I just happen to take, okay, this f of z around this pole at z is equal 0, I will end up with actually not f of z, I will end up with f of z plus 2 pi I. In this case, if I take another loop, I will end up with another 2 pi I. So in this case, I will get always an additional of 2 pi I, 2 pi I, 2 pi I. And the group will become, and the monodromy group will become cyclic with the generator 2 pi I. So this is the history. So this is the story behind the monodromy, the main idea. And the point is that a wave matrix, when it turns around these singularities following a path, m gamma, gamma, it will end up with a matrix m gamma that will come into play with the monodromy. So my point is that I would like to deform the system while keeping this m gamma fixed. So this is the point behind, this is the idea behind. So this observation is actually key also for another thing, which is the characterization. This characterization is key for the representation of the fundamental group. You guys might have guessed that actually taking loops around singularities, this will give me something about, this will tell me something about the fundamental group. And this is super clear because when I get a matrix going around the pole, what I'm going around really are the generators of these gamma, these laces around the poles. They are really the generators of the fundamental group of the surface. And when I get a matrix from these poles, what I'm getting also is a representation of the fundamental group of the surface. So these monodromy matrices are actually representations of this fundamental group of the surface. And this builds a map from the moduli space of connection that I'm going to explain a little bit more later when I introduce the definition of a connection to the moduli space of representations of the fundamental group. So it's really a map, which is called the monodromy map, by the way, from a space that is completely algebraic to a space that is completely on the other side topological. And this is the fascinating thing about this. This monodromy map was proven to be actually symplectic in the works of Philippe Bolch. And this symplectic nature is now referred to as we now know how this actually manifests. And it actually is called now the symplectic nature of the fundamental group. So now that the basic setup is set, I would like really to see what is actually the relation with the Pain-Levé equation. Because as far as I'm concerned, I did not mention anything about the equations and anything. I mentioned that you get some very fruitful applications, and those applications are going to be related to the Pain-Levé program. So let me explain a little bit what is actually the Pain-Levé program. So in the end of the 19th century and the beginning of the 20th century, there was a very common problem in analysis, which goes as follows. So define an algebraic equation and look at its solutions. And you can define actually new transcendental functions, so functions that you don't know how they react, and you cannot express them in terms of classical functions just by taking them as solutions of some algebraic equations. And it became really a business back then that, okay, I could define a new equation, and this equation will give me some transcendental functions. So this is the story. This led Pain-Levé and his students to initiate a program called the Pain-Levé program, which classifies these ODEs. Okay? So these ODEs are classified in terms of their solutions. So two ODEs are the same when it comes to when the solution is actually similar, when the solutions are actually similar or related. And the program was completely solved for the first order equations, so first derivative equations. And the program turned to be super more difficult, way more difficult for order 2 equations. However, for rational coefficients, so when there is only a double derivative in the solution without a coefficient in front, the program was solved and gave three actual solutions, three actual possibilities. So first, the equations that can be integrated by quadrature, second, linear equations, and third, 6 new equations, which are now called the Pain-Levé equations. And the link between the system that I considered before and these Pain-Levé equations, these 6 Pain-Levé equations, is that the Pain-Levé equations are actually conditions that could be set on the matrix L that gives the compatibility of the system. So this is the story behind. So the Pain-Levé equations, they are actually can be obtained from systems using the matrix L of Z and the wave matrix psi that I used before. So this is the story behind. And Schlesinger and Fuchs, and the first equation was actually discovered by Fuchs also, which was the Pain-Levé 6 equation. And then the other equations followed after. This was also done because of a formulation of the Pain-Levé equations. It is the Hamiltonian formulation. So if you have a solution of it was Malmquist who formulated this. If you have a solution Q of t of a Pain-Levé equation, you have always the existence of a function that is called the Hamiltonian, which gives you Q and a dual coordinate called P also. And this was the link to also symplectic geometry and Hamiltonian geometry in relation with complex mechanics. So This is more or less what we are gonna get when we solve the system that I'm gonna consider later. So the big so the big picture is the following. The system that I have considered before is just a system that it could be seen as a connection on a vector bundle. So for the system that I've considered before, there is always a trivialization of the bundle, okay? But the abstract notion is that we have a connection, which is in the space of Diram, so Diram connection. And this gives an isomonodromy system. I will explain in details when we see an example. You might see that, and now I'm just mentioning a lot of names and mentioning a lot of structures and a lot of results. It is true, but on the example, you will be able to understand more or less the story behind. So the story also goes way more to a classification problem, which was initiated by Hitchin, and what he wanted was a classification of all integrable systems. This is the LAX project, and this is a very large question, and you cannot do that very easily. What he did is consider a curve. So in my case, the curve is always going to be the Riemann sphere with a point at so C with a point at infinity, and he equipped this with a hyperkähler manifold, considering a hyperkähler metric, and he defined out of this, through the Hitchin equations, he defined Higgs bundles, meromorphic connections, and then through the Riemann-Hilbert correspondence, he was able to attach also the character varieties, or in the simple case, the fundamental group that I talked before about. So the first two correspondences between M-dol, which is M-dolbo for Higgs bundles, and MDR, so MDRAM, for connections. This is the non-abelian Hodge correspondence. This is the story behind it. And then the correspondence between a connection and character varieties, so fundamental groups, representations of fundamental groups, is the Riemann-Hilbert correspondence. Combining these two correspondences, you get the general picture that is above, and you get really the theory of the non-abelian analog of the Hodge theory that we have. You will see in the example that I will treat, we are going to work literally on the moduli space of Diram, not more than that. Solving an example in this theory is already a huge achievement, honestly, because things get really, really messy and it gets really difficult after. But more or less, this is the general picture that one wishes to extend and then wishes to understand. So this picture is really also based, so it was initiated by Hitchin. However, Carlos Simpson also worked on this. Simon Donaldson, Corlett, Kevin Corlett, Kono, a lot of people, Philip Bulch, Daisuke Yamakawa, a lot of people worked on this actually on different aspects. And this picture is just the outcome of several results. So this is the story behind. And me, I will restrict myself to, again, the moduli space DRAM, the DRAM moduli space, which is the moduli space of connections. So I will just get to the definition of a connection that I'm going to be considering. It is the following. So I will fix a divisor. I will fix some orders of the poles. And I will fix a connection to be seen as just an operator that acts on V with the poles bounded by the divisor, which takes values in V twisted by the sheaf of sections, literally V times K of D. Okay, satisfying, very necessary, the Leibniz rule. Upon choosing a trivialization, this will just, and considering solutions of the system, this will just be the system that I considered first. So I'm always restricting myself here to the trivial vector bundle. So this definition here, it's a general definition that goes on any vector bundle, on any principal bundle even. But me, I will restrict myself to the trivial vector bundle, and I want it to be trivial always in order to facilitate, to make easier the computations and to make easier the things that I'm going to be considering. but more or less, there are way more general settings. Me, I'm restricting myself to this explicit setting because I need explicit formulas later. So this is the story behind. And the motivation behind considering this simpler case of the above definition is just to understand two things. So first of all, the classification of Frobenius manifolds done by Dubrovin of semi-simple Frobenius manifolds, and then to understand the isomonodromic deformations of the equations of the Japanese school of Jimbo, Miwa, and Ueno. So this is the story behind. I will restrict myself to a given side. I will even restrict myself even more to the to the rank 2 setting. So literally, I will have matrices only 2 times 2 matrices. I will have only 2 solutions. So if I regroup them in a matrix, I will get a matrix of 2 times 2 of 2 times 2 entries with 2 times 2 entries, and I will be able to restrict myself tremendously. However, guys, even with this restriction, there was never actually general formulas for the general theory behind. So this is what I'm going to be considering next after motivating why do we need actually these explicit formulas. So why do we need actually explicit formulas if we know that actually we have the symplectic nature and the symplectic structure? So first of all, to make connections with mathematical physics and with other domains, we need these explicit formulas we need these general explicit formulas with the general orders, with the general pole structure, with general things. And although the setting that I'm considering is already super restrictive, this gives very fruitful links to wall crossing, Painlevé transcendence, duality of Painlevé equations, the duality of isomorphic deformations, and we're going to be able to see these applications in the example that I'm going to be giving. So it helps also extend the knowledge that we already know, because when you have the equations, it's always easier to manipulate things and always easier to see the limits and things to get. So this is more or less, also it helps build bridges between these approaches. So we have another approach which is available in the literature using loop algebras and seeing the lax matrix L of Z as actually a loop algebra instead of like an element of loop algebra rather than just a connection on a vector bundle. So these explicit formulation helps us seeing that, okay, we can combine the two approaches actually. This is also something that I'm going to be explaining next. So I hope that I convinced you at least that this actually is important, although some things are already known from algebraic geometry. So let me now go to recent developments and the results. And for that, I'm going to be needing to change the slides to a presentation that I gave also recently, which is actually this presentation. So first of all, rational connections in GL2C. So the word rational itself means that I'm considering connections over the Riemann sphere. So my local coordinate is going to be always in C with infinity as a pole. Okay. So I'm considering this space of connections, which is FRR. I'm fixing an arbitrary order of poles. This is exactly the matrix that I've considered before. And I'm considering modulo the quotient action of GL2C, where GL2C acts by conjugation simultaneously on all coefficients. Okay. So this is my main definition. This is just the thing. So another short version is to see it as just a rational function with fixed poles, of course. This space is actually turns out to be a Poisson manifold. This is one of the applications of the isospectral approach. So the loop algebra approach. This is a Poisson manifold. We can guess the dimension, we can guess the Poisson structure, and we can build also Poisson maps from one side to the other. So it's very fruitful. However, I will not go in this direction exactly. I will go into another direction, which is the conjugation action of GL2C, of the reductive group. So upon choosing a trivialization of the bundle, my system is going to be like this. So you may ask me, okay, why are you now using lambda rather than Z? Well, lambda is just thought of as the local coordinate. So around infinity, it's going to be minus, so it's going to be z is equal lambda minus 1. This is why I'm now using lambda rather than z. And you will be able to see that very soon in the next slide. So this defines the rational connections on GL2C. Psi of lambda are called the horizontal sections or a wave matrix. And the L of Z is called the lax matrix. So the quotient action of the reductive group can be seen actually because if I consider a gauge transformation that would change, so a gauge matrix, G of lambda, that would change the horizontal section, I could get another solution which is similar to the solution that I have before. Literally, however, it should be with L hat of lambda, what I define literally under, which is going to be literally given in terms of the initial lax matrix with some combination of the conjugation action. So this is why it is important before to quotient by GL2C in order to eliminate the connections that are going to give the same solution. So two connections are isomorphic when they are related by a gauge matrix. Okay. So one very important aspect of this, of the theory, was developed by Birkhoff. And it's actually known until the moment as the Birkhoff factorization or the formal classification of meromorphic differential systems. So if I consider L of lambda such that all coefficients have distinct eigenvalues, so I'm going to stick to this to distinct eigenvalues. However, I will tell you later what happens if it does not, if it's not generic. So if the eigenvalues might be not the same. So at any pole xp or infinity, there exists a local gauge transformation or a formal bundle automorphism also, such that psi of xp locally is given by the following form. With the local coordinate, as you can see, of z infinity of lambda. And psi regular is regular, of course, this is why there is a reg on top. So upon this, we can get the form of this G infinite, the GXP of lambda. And we can act with it through the gauge transformation of before here on below. We can get the form of the lax matrix around each pole. And this gives us a set of matrices, a set of coefficients, which are the TP, which is literally the residue of the matrices at these points. This gives us two sets, which are TP, if you can see, TP1K, TP12K, and TP10. These sets are going to become very important sets because in the next slide, I'm going to say that these sets are actually the monodromies and the deformation parameters. So this local diagonalization is actually called Birkhoff factorization, formal classification as well done by Birkhoff, Turretin level fundamental form, or formal normal solution, literally. So when the matrices are not diagonalizable, which gives us the Pan-Levé-1 equation, this has to be a little bit changed, but the analogy follows exactly the same in the same way. So there is no need to worry about this. So this diagonalization, as I said, gives me two set of parameters. One of them is the TPK with k bigger or equal to 1. Which is going to be deformation parameters, the parameters on which I'm going to deform the system, consider isomodromic deformations, while keeping the other parameters. So TP0, I'm going to keep them intact. So I'm going to keep them really preserved. And this is what's going to generate the applications later. So, of course, as I said before, the RP is equal to 1 are called the Fuchsian singularities. Construction for even higher rank connections is similar. However, there are several ways, depending on the Jordan blocks, of how to do the things and how to generate the things. So it's a little bit complicated when it comes to higher rank setting. And this is really the rank 2 setting, which is the simplest. But things could get really tricky even here. The rank 1 setting is actually related to the Frobenius manifolds, but I will not go in this direction as well. I will continue in the rank 2 setting for the moment. I will talk about generalizations later and open problems, and I will mention this part actually. So the general picture is the following. I have now, if I fix these coefficients and these monodromies, I will get literally the moduli space of connections. That is actually two Lax matrices are isomorphic when they are related by gauge matrix. So in this setting, I'm really fixing the T and fixing the T0. So my connection is really fixed. Not completely though, because I will have additional coefficients that I need to define, which are the Darboux coordinates. So this moduli space is a symplectic manifold of a given dimension, and the dimension is 2G. So G is actually the genus of the spectral curve defined by the algebraic equation determinant of y2 minus L of lambda. So it's a degree 2 curve, which is a double cover of the Riemann sphere. However, this double cover has a special genus, which is the genus of the spectral curve, and defines the dimension of the symplectic manifold that I'm having. So the Lax matrix is completely determined by the poles, irregular times monodromies, and 2G coefficients that I will define later that are Q and the Q's and the P's, the Darboux coordinates. I believe some of you are now wondering why is that these Q's or P's are going to be the solutions of the Panevet equations later. Well, yes, absolutely. These Darboux coordinates are going to be exactly the solutions of the Panevet equations that will come later as results. And this construction actually gives us this setup to consider isomonodromic deformations and to prove that they are Hamiltonians later. So before proceeding, one could actually also go into what we call H-bar connections by simple rescaling. So let me be super clear here. Geometers, so people that consider geometry, they are not really interested in the H-bar parameter that comes to play. However, when it comes to physicists and mathematical physics, people tend to give extra attention to this H-bar parameter because it really defines a lot of properties, and to make connections explicitly with topological string theory and quantum field theories. This is what you need to consider. However, for people following only geometry, I repeat, you can fix completely H-bar is equal to 1. There will be no problem with that actually. For the rest of the talk completely. I will still be considering the H-bar parameter just to make connections with mathematical physics. However, you can fix it to 1 whenever you see that there is actually an ambiguity or a problem. So just to summarize the construction of an H-bar deformed or without the H-bar completely rational connection, Lax matrix in GL2C with given polar structure. One uses the local diagonalization or the Birkhoff factorization in order to fix the connection in terms of the location of the poles, the irregular times, and the monodromies at each pole. And then as one gets the deformation parameters, which are the TPK, and the monodromies that we would like to keep intact and we would like to keep very clear, if we deform the system following these times, so these T, one get an additional system that is literally so if I deform the horizontal sections, the solutions in a certain way, in an admissible way, in an isomonodromic way, I will get an additional AT matrix, which will come to play a role in this construction. Combining the two systems, so literally the del lambda psi is equal L psi, and this system with the horizontal sections, one get the compatibility equation of the system, which is given by this equation. Solving this equation actually will give me all the needed construction and all the needed things that I need to do, all the manifestation and all the symplectic structure behind. So L and A together are called the Lax pair. So when I refer to a Lax pair, I refer to both L and A together. So the next step is to define Darboux coordinates and express the Lax matrix and the and the auxiliary matrix, so the Lax pair, in terms of these coordinates, irregular times and monodromies, solve the compatibility equation to obtain the Hamiltonian evolutions of the Darboux coordinates, and obtain that these evolutions are indeed Hamiltonian, reduce the deformation space to only g non-trivial directions to get Arnold-Reville form of the Hamiltonian system. This is because, so the last point, I will explain it in more detail. This is because when you obtain the Hamiltonian, you realize that the Hamiltonian is way bigger than you anticipated and actually contains way more dimensions than the actual moduli space. And you cannot allow that. So what you do is use the theory of Hamiltonian reduction by following group actions. And you use the group of Mobius transformations, the projective group in our case, it's PGL2. Or if you do the reduction, it's going to be PSL2. And you get literally the Mobius transformations to reduce your Hamiltonian completely, and you get exactly what you need at the end. So let me proceed with this. First of all, let me tell you that solving the compatibility equation itself, attacking it completely, actually gives a lot of problems. So gives a huge amount of problems, and you will get four equations that are almost impossible to solve. So if one could just use something to make easier this task, one would take it completely every day of the week. So this is why one defines a gauge matrix given here, 1, 0, L11 and L12, which gives me an upper form for the matrix. Upper form, it means the first part, the first line of the lax matrix is going to be determined only by the second. So the lax matrix completely is going to be determined only by the second line. And this will leave us in a very suitable place, because this will get us also the quantum curve, which is an R module, by the way. And this will get us only to solve two equations for the compatibility equation to be completely done. They are recorded in the next slide. So in this gauge, so these are the two equations that I'm talking about, actually, here. And we will get only two equations to solve in order to solve the compatibility equation completely. This is way better than solving four huge equations. This is first. And in this proper gauge, the Darboux coordinates are actually the apparent singularities. So it feels super natural for us to take this gauge and solve the Darboux coordinates in, and take the Darboux coordinates in and try to solve the equation in them. We complement the Darboux coordinates by the dual coordinates defined on the spectral curve or defined through the residue formula, the residue of L21. And our next goal is to consider general isomonodromic deformations, so literally with this operator, L of lambda, and go to solve the compatibility equation given by these two entries, literally. And this supposedly will give us Hamiltonian evolutions of the Darboux coordinates. So expression of the Hamiltonian Slack matrices in the upper gauge. So first of all, I will give you just the results that we were able to get in the upper gauge. You do not need to consider isomonodromic deformations in order to get the explicit expressions of the lax matrices in the upper gauge. You just need the formal fundamental solution or the formal classification in order for you to get the explicit formulas. So for R infinity less than or equal than 2, special treatment should be done, but it's not unmanageable. It's doable, I would say. But you have to pay attention really for the order of the poles, because whenever a pole order changed, everything could get really a little bit messier. So this is more or less what I get for the matrices, expression of for the lax matrices in the upper gauge. So this is normally what I get. Okay, expressions are horrible. I agree with you completely. However, keep in mind that these are for general, so for really general solutions and for really general polar structure. So I'm considering an arbitrary order of the pole. I'm considering an arbitrary polar structure with whatever XP that I'm taking, with whatever pore I'm taking. And this is what you get also for the coefficients HPK. So you get also Van der Waals matrices, of course, and the coefficient, and you get that the coefficients HPK, which are very important coefficients later, depends on the whole polar structure, not only pole by pole. So this is what I'm saying, that when you change the polar structure a little bit, you change the whole structure behind, because every pole plays its own role inside. And the whole polar structure is dependent on every single pole, not just like it's an arbitrary dependence, like it's, oh, okay, I depended like on every pole singularly. No, there is a contribution of the whole polar structure inside. And this is what makes this really difficult sometimes. You get the van der Waals matrices in function of the Darboux coordinates. And when considering isomodromic deformations, you consider general operator of the expressions that we have before in order to get exactly what you need after solving the compatibility equation. And what you get is that the Darboux coordinates have Hamiltonian evolutions, that's for sure. So literally from here, from this amount, so once you get the evolutions of Darboux coordinates, it becomes just a simple task to get the Hamiltonian, and you get the Hamiltonian to be this. From the shape, you can immediately guess that actually this is terrible, and this is not the Hamiltonian that I was getting. When I got first this expression, I was using a software, of course. It was a little bit horrible, I have to say. And it was not a very good thing because the coefficients are not easy to express. You see, the coefficients are really, so the coefficients in red, for example, the news, the C infinities are not very easy to express and are not super fun to play with, honestly. So you get this, um, which is also as horrible as ever. Um, However, you get that some coordinates, some coefficients, for instance, the news, are independent of the Darboux coordinates. And this gives immediately an identification of the Hamiltonian. And this gives actually, if you are a little bit into this, you could see that actually some part of this Hamiltonian is going to get completely wiped out later. And this is what we're going to see later. So those are the additional matrices, no triangular matrices. So some properties induced by this. So the first paper that we got, the first result that we got from this construction is that there exists a birational map between the Jimbo Miwayuno school, the Japanese school, and Philip Bulch that contributed to this, and our symplectic isomonodromic connection. So we have explicitly the gauge transformation that takes us from one side to an explicit formula that gives us the explicit dependence on all the coefficients. So the Hamiltonians, roughly speaking, are time-dependent linear combinations of the isospectral invariants, the HPK, the independent of deformation. These invariants are super important because they make the link also with the isospectral approach, which is the other side of the coin, literally. So increasing every order of the pole is like increasing the size of two upheld matrices that I considered. For Fuchsian singularities provide only a simple contribution, literally simpler formulas as known from Schlesinger, literally. But as I told you, so this thing that we have a very general Hamiltonian that contains a lot of directions, and the directions are not exactly the same size of the moduli space, was actually bugging us, and we were like, okay, there might be something related to the symplectic reduction of using group actions of Hamiltonian systems to get an Arnold-Liouville form. So this was the next step that we actually did. And a theorem by Darboux tells you that actually when you have a simple a linear dependence on the linear evolution of Darboux coordinates, you can always find a symplectic change of coordinates that will eliminate this direction or this evolution. This was exactly what motivated us to define these shifted Darboux coordinates, for which a lot of evolutions got canceled out, actually. How did we do this? It's just by following the action of the Mobius transformation on the connection itself. So we were able to define these new set of times, T1, T2, the big T's, and we called them trivial times. And we defined one or tau. In our case, there are many taux, of course. that will actually be the isomonodromic time, through in which evolution will give us the Painlevé equations. So the evolution following the isomonodromic time will give us the Painlevé equation, will survive and will give us the Painlevé equations. So literally what I've been saying, there exists a one-to-one map taking us to the new set of to the new set of to the new set of times. So these big T's are called trivial times, which means that the evolution of Darboux coordinates is actually zero following these times. The Hamiltonian evolution actually, after this reduction, simplifies tremendously, and the Hamiltonian following a direction will become only this. So literally the red part survives, and the additional part is literally taking away. So what remains is that, okay, since we have some trivial times, which means that if we take some values for these trivial times, this will not change the symplectic structure behind. And this was our next step. So literally, let's take canonical choice for the trivial times, for the big T's, in order to get rid of them and to get more explicit formulas. Before that, we proved an additional result that since our Hamiltonian is time dependent, so on the isomodromic time, we have to consider, instead of the symplectic form on the surface, we have to consider an extended symplectic form. This is what we considered, and this, with the Hamiltonian, identifies completely the symplectic manifold that we are taking, so the moduli space, and identifies completely the symplectic structure defined up top. So this is what we have done, and we have showed as well, following direct computations, that actually this symplectic form also simplifies following this symplectic decomposition. So following the action of the Mobius transformation. This gives us explicitly the Arnold-Liouville form that we wanted to get. We as well performed an additional reduction, which is going from GL2 connections to traceless connections, so literally to SL2. So this is already known. However, this reduction of the two form was never known before, and we were able to prove that actually the action of the Mobius transformations, they get the symplectic structure to be completely simplified. So what was remaining at the end is to give values to consider the applications. So literally to consider the polar structure, to fix the polar structure at certain thing. So first, if we consider n is equal 3, and we consider all the poles to be equal to 1, so which is the Painlevé, this gives us the Painlevé 6 case. And we were able to get exactly the canonical reduction of the Jimbo Miwa of the Japanese school. We considered other examples, for example, Painlevé 5, Painlevé 4 case, the Painlevé 3, Painlevé 2. We considered the full Painlevé equations, all the 6 of them. So now we have only 5 Painlevé equations because the Painlevé first is actually a twisted case. But we are also able to do that. So we did that also as well in a different paper, in the second paper. And we were able to do also the symplectic reduction on the twisted case. So the twisted case is actually so particular. Why? Because you get a ramified pole. You consider a ramified pole at infinity, and this changes completely the formal normal solution. So the starting point of our consideration. But other than that, the things are the same. The construction, the following step by step are actually the same. So this is what we were able to get, and we were able to get the full family of Painlevé equations. So from Painlevé 2 to Painlevé 6 for the generic case, and also the Painlevé 1 hierarchy in the twisted case. The Painlevé 1 hierarchy completely, actually. When you go up with the order of the pole, you get a higher Painlevé transcendent, so literally the Painlevé hierarchy. So until the moment, this is the first result that I wanted to go through. Now I'm going to go for another result, actually, that is related to the isospectral approach. But before that, are there any questions on the first two parts? So for the rest, I will really go super fast on some aspects of the formulas and explicit formula that were built in the geometric construction. So the main story on the other side, when we published the first two articles that we had on the other side, there were some works on the isospectral side, which is the other approach used actually here, which are used on the Dolbeault side, so Higgs bundle side. They are used there in order to have also integrable systems and in order to have also the classification of integrable systems. So the story of isospectral deformations goes completely different. It's a completely different construction. It uses actually the loop algebra structure. So a Lie algebra, a tensor, actually a ring of Laurent polynomials. And you can see actually the lax matrix as an element of this loop algebra, actually. And you can get the Poisson structure out of this. So, and the story behind is that you consider this system in order to satisfy, sorry, in order to satisfy the isospectral condition, which is this condition in red. So you would like to build two matrices. One of them is L, the other one is the A matrix, which are the lax pair, that actually satisfy this. And you want to build the structure considered behind, the structure considered behind. However, this is no easy task because although the isospectral coordinates U and V, they exist, this was proven recently in 2022. Although they exist, it's very difficult to get actually a hold of these coordinates and to define them. So in our approach, as you have seen, the Darboux coordinates are defined as the apparent singularities in the upper gauge. For them, they do not have a true definition behind. They have to track everything down until the end, and at the end, they have to actually choose some coordinates, an arbitrary choice that will get them the symplectic structure and the integrable systems that they wish to have. So this is the problem behind, and this is what we tried to remedy, or we tried to have when we considered our third work, linking the isospectral and the isomodromic approach. So for this, we needed a change of coordinates that is actually not easy to find and non-trivial in the sense that it's going to be actually time-dependent and non-symplectic. So the symplectic structure is going to change, and the time dependence is gonna change things also. So it's going to be way more difficult to get the symplectic structure. However, the systems are both linked through this change of coordinates, which is not time dependent and non-symplectic. So, and this is what we got. We got a differential system to solve as function of these two coordinates, and we got actually a system of functions that relates to approaches. So what is the interpretation of this? Why is this system actually, and why is this two change of coordinates, these two coordinates games are actually not the same and are actually time dependent and non-symplectic? Well, this is because the map between M Dolbeault, so the space of Higgs bundles, and the space of connections MDR is actually, in some cases, not isomorphic, but actually diffeomorphic. So the map between the two could be a diffeomorphism and should not be actually a symplectomorphism that identifies the symplectic structures between both sides. And this is exactly what we got in this case. We got that the symplectic structure that is actually mapped from the M Dolbeault, so from the space of Higgs bundles to the space of connections, was not a symplectomorphism, and this was manifested by the system which was supposed to be solved, but we were not able to get a closed form of this, and we were able to give a manifestation of this diffeomorphism between the two sides in order to get actually a system that is actually, in order to get from one coordinates to the other, from one system to the other, we needed a symplectic change of coordinates, a non-symplectic change of coordinates, sorry. And this changes the whole game. So this was one of the also another results of the construction that we did and that we had. So finally, I will talk about the duality in isomodromic deformations and about some open problems. I will mention one of the results very fast that we got in the last article that we published, and then literally talk about just the open problems that occurs. So you have seen in my talk actually one concept that I used was the spectral curve defined by the determinant of y minus L of lambda. Okay, so the characteristic polynomial literally. Defined through the definition of L of lambda, literally a connection or a lax matrix. So if you define the spectral curve, and then you take these two coordinates that are lambda and y that define the spectral curve completely, and you swap one with the other, so you swap the two, you get another spectral curve. And you get completely another spectral curve because one spectral curve on the first side, you can consider a degree 2 spectral curve in y and the degree 4 in lambda. When you swap them, you get actually a degree 4 spectral curve in y and a degree 2 in lambda. So these are completely two different things. They are not even related as far as I'm concerned because the degree is completely different. Well, it turns out that actually this swap preserves the symplectic structure behind. So under the swap, there is an identification of the irregular times of the monodromies of the spectral sides. And under this identifications, the Hamiltonian structure of both sides are completely the same. So you get two symplectic structures completely different. You may tell me, but this is a little bit weird because the spectral curve with degree 2, for example, it comes from a rank 2 connection. And you are telling me that you can swap the lambda and y in order to get a degree 4 spectral curve, which is a rank 4 on a rank 4 connection, defines a rank 4 connection. So connection defined on rank 2 and connection defined on rank 4, for example, could they give the same symplectic structure? And the answer is yes. What we considered is this. We considered actually a rank 3 connection defined on a trivial vector bundle also. And we showed that actually, if we swap the x and y, we get actually the same symplectic structure behind upon an identification of the trivial of the times and of the trivial or non-trivial of everything in terms of the spectral curve. So as long as the spectral curves are identified, you could get a complete analogy between the symplectic structures. So the history of this duality is it's called the XY duality. So you swap the x and y of the spectral curves. It appears actually in topological string theory, symplectic geometry, moduli spaces, a lot of places actually. And for algebraic geometry, these people they call it the Fourier transform. So it was that John Arnaud that considered first this Arnaud's duality, and that showed it on a case. Other people also tried to see the reason why. Woodhouse is one of the main articles that I love about this, using the middle convolution also method that some people also were able to get some results. And in particular, Philip Bolch was the one that extended this in his article, Simply Laced Isomonodromy System, was able to extend this to a group action. Literally, in Publication Mathématique de l'HES, the article is, and it's a fascinating result that links declassification of isomonodromy systems to Dynkin diagrams and to affine Lie algebras. So you get Dynkin diagrams actually that identifies the connections that you have. So our result, what we had, actually extends this structure of Philip Bolch because we consider a higher polar structure. So for him, he considered simply laced, which means that he considered the pole of maximum order 2. This is the maximum that he considered. However, for us, we consider the polar structure of R infinity is equal 3 in the rank 3 case. And this is what we were able to prove. We were able to prove that actually two structures under the identification are the same. And the result that we had was this, actually, this is a huge table. So one side, it's the GL2 connection. The other side is the GL3 connection. And we built literally maps, dualities all over the place in red. Um, Literally identifying the symplectic 2 form, the reduced symplectic 2 form, the Hamiltonian structure, the reduced Hamiltonian structure, following the same construction that we have done. So more or less, this was the theme of the last thing that we have done. Um, of the last thing that we have done and the applications to that. It's I can enumerate some applications that we mentioned inside the article. Some of them are literally, for instance, matrix models, topological recursion, symplectic geometry, enumerative geometry, and Gromov-Witten invariance. A lot of applications that could go actually very like wide with the applications. But it depends. It really depends on the application that one would look for and to specialize this direction of the work. So this is more or less our goal was to prove that two structures are actually could be actually the same. And the question that one would ask completely, so there is no actual proof of the duality until the moment. So there is no actual proof that the duality is works for every connection. There is not no such proof. And we have solved it just on a case, not on the general case. So the point that one would ask, actually, are there some other dualities that one could consider? So what are the symmetries of these moduli spaces of connections? So these MDR. So if I exchange X and Y inside, it works. The symplectic structure works. This should be the same on the Betty side, except that you don't have coordinates there, and it becomes super difficult there. So what are actually, could I build a diagram like in relation with Nakajima quiver varieties or something like this that identifies completely the symplectic structure? And this is the question that I was writing recently in my thesis. And this is the actual like question that I would like to take part of later. So this is a very huge question, of course, because it will classify all problems all over the place, all integrable systems. And some people have tried already some things. Philip Bulch already tried uh, Dinkin diagrams, but it's not that easy. It's not that easy to get. And I believe there is a hidden structure that it's actually one needs to take care of. And this is the problem that one wishes to get. So at the end, I would like to thank you so much for your attention and for the invitation again for the seminar. It has been a pleasure to give this talk. So thank you so much.